Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we continue the discussion of reflections and transmission from a multi-layer cavity using the S matrix approach or the matrix approach that we discussed. And before we go to the multi-layer case, we consider a single film having two interfaces, and this single film is actually widely used in spectrum analysis in the optical frequency range, and this is known as a Fabry-Perot cavity. This in fact is also used as a fundamental design of a laser cavity. So what is a Fabry-Perot cavity? It was actually built by the scientists Fabry and Perot, and the cavity essentially consists of a single medium, so maybe a glass tube having glass of refractive index n and surrounded by a medium of air. Okay. In a practical version of this Fabry-Perot cavity, you can even see that there is actually a short mirror. Okay. So that could be a simple glass substrate on which you have coated some metal so that it will actually act as a finite thickness mirror, and then you have another mirror out there, and then in between region you can either fill with a medium or you can again leave it as an empty kind of a thing. Okay. Usually you fill it with a medium of refractive index which is larger than air. Okay. They can also be used in buried inside other media, but Fabry-Perot cavity in optics and optics experiments are more or less carried out with air on both sides of the mirror. The mirror thickness we will ignore in this discussion, but one should actually consider the thickness of the mirror when designing an actual Fabry-Perot cavity, because it does influence slightly what we are actually about to look at, the performance metrics of the Fabry-Perot cavity. Okay. So you have these two mirrors. Okay. The mirrors actually have a very large reflection, so which means if I remove the second mirror and then shine light from one side, then most of the light is actually reflected. So very little of the light is actually transmitted into the second medium. Similarly, if I consider now, what happens is that if I actually bring in one more mirror and then adjust the spacing between the two mirrors, okay, I am assuming, as I said, very thin mirrors. If I adjust the spacing between these two mirrors, then if we choose a particular spacing, okay, which we will derive shortly, then it is possible that although these two mirrors are in general reflecting very high reflectivities, you can see that the entire incident light could be transmitted into the second medium. So you can see that you have two mirrors. If you appropriately space them, then the entire incident light can be transmitted. Okay. So we analyze that by using the approaches that we have developed and the equation that we have seen in the last class. Because this consists of a single film having two mirrors, you will have two matrices S1 and S2 that we saw in the last class. For simplicity, we will assume only normal incidence, although we will later show you what happens when you have a obliquely incident light on this Fabry-Perot cavity. Okay. So we immediately recognize that the reflection coefficient from the air to the glass interface can be given by 1 minus n by 1 plus n for the normal incidence, and from glass to air the same reflection coefficient will be given by n minus 1 by n plus 1, and if you examine R1 and R2, clearly R2 is minus of R1. Okay. So we derived an equation in the previous module, so where the overall reflection coefficient R was given by, and this is the reflection coefficient in terms of the power. So this capital R was related to the overall reflection coefficient gamma square, okay, or small r square, does not matter. So this was equal to R1 square plus R2 square plus 2 R1 R2 cos of 2 delta 2, because I am assuming that the thickness of this medium is D2, delta 2 will be equal to K0 N2 D2, where N2 is actually equal to N, which we have taken glass in our example. Okay. So this was the numerator. In the denominator you have 1 plus R1 square R2 square plus 2 R1 R2 cos 2 delta 2. We have so far not made any assumption on D2, we will do so shortly. But look at this, since R2 is equal to minus R1, you can substitute for this value of R2 in this expression and then simplify the expression. Okay. So when you simplify the expression, which I will leave as an exercise for you, it is couple of steps only. So substitute R2 is equal to minus R1, so square doesn't really do anything to this, but R1 into R2 will have a negative sign now, and R1 R2 in the denominator will also have a negative sign. This term R1 square R2 square will be R1 to the power 4. Okay. So if you put in all those values and then employ the a square plus b square or a minus b whole square kind of a formula, then you can write the overall reflection coefficient as 4R1 square divided by 1 minus R1 square whole square. Okay, you can see that, and because there will be a minus in the sign of R1 R2, you can show that in the numerator you will have 1 minus cos 2 delta 2, and then you can use the trigonometric identities to replace that 1 minus cos 2 delta 2 by sin square delta 2, and then you can do the same thing in the denominator. So in the denominator you will have 1 plus 4 R1 square divided by 1 minus R1 square whole square times sin square delta 2. If we define f as a factor which we will call as finesse of the cavity, so the larger the value of f, the higher will be the transmittivity and narrow will be the bandwidth, as we would see. Okay. So this finesse of the cavity can be defined as 4r square divided by 1 minus r square to the power 2, okay, where I have taken r1 is equal to r for simplicity. Okay. So instead of carrying r1 all the time, I have just taken r1 is equal to r. So if I have a finesse of the cavity defined in this way, then the overall reflectivity, which is the amount of the power that is reflected back to the power that is incident, is given by f by 1 plus f sin square delta 2. Okay. Now I am interested in the transmittivity, that is how much power I am able to transmit out of the Fabry-Perot cavity. Okay. So that can be obtained by this relationship, which tells you that the total power must be conserved for a lossless system. So 1 minus reflectivity must be equal to transmittivity T, and this will be equal to, I obtain 1 by 1 plus f sin square delta 2. Okay. So this is a transmittivity that I obtain, and you should understand that this transmittivity is actually a function of this quantity delta 2. Okay. And we have already seen delta 2 is nothing but k0 n2 d2. In our design we have few choices. For example, I can actually vary this d2 in order to make this sin square delta 2 go all the way from 0 to 1, correct. So if I choose this quantity d2 for the same value of k0 and n2, and then plot what happens to the transmittivity as a function of varying delta 2, okay, assuming reasonably large value of f or the very high finesse, then you can see that when delta 2 is equal to 0 or it is going through an even multiple of 2 pi, right, or any multiple of pi in fact. So because in any multiple of pi, sin square of pi will be equal to 0, and that quantity in the denominator will be equal to 1, numerator is anyway equal to 1. Therefore the transmittivity at the value of say some odd multiple of pi for delta 2 will be unity. Okay. So it would be 1, and then it quickly drops off and goes to 0. Okay. That whether it goes to completely to 0 or it stays slightly above, that depends on the finesse f. Okay. When delta 2 is away from m pi, you will see that the reflectivity, when you know sin square delta 2 is equal to 1, the minimum reflectivity that you are going to get would be equal to, or minimum transmittivity that you are going to get will be equal to 1 by 1 plus f, right. And when f is much larger than 1, then this quantity can be approximately 0. If f is not very large, maybe f is just 2 or 3, then you will see the curve to be slightly different. So it would be a curve that would look like this, but with this f much larger than 1, you will actually see that the curve almost goes to 0, and most importantly stays flat until it reaches the next peak, which happens at m plus 1 times pi, where m is a integer. The same condition applies on the left hand side as well. Assuming again f to be much larger will allow you to see that the reflection remains, or sorry, the transmission remains close to 0 and then picks up at some m minus 1 into pi. From this you will see that there is actually a periodicity. The periodicity is of the in terms of periodicity of the transmission coefficient is about pi in terms of delta 2. Okay. Now we have already seen that f must be much larger than 1, so that the peak here, which denotes the transmittivity around this particular value of m pi, should be as sharp as possible. So if you want a very sharp peaked transmissions, then you want to keep f to be much larger than 1. Now how do I make f larger than 1? Remember, f is nothing but 4r square divided by 1 minus r square to the power 2. So clearly for f to be much larger than 1, r must be approximately equal to 1. Okay. So this is a very interesting scenario where you actually take a very high reflectivity mirror, okay, and then you somehow put one more high reflectivity mirror, and the result is a total transmission. So almost no reflection and an entire transmission into the or outside this cavity. Okay. Of course, for that to happen, you should choose delta 2 such that this is an odd multiple of m pi. But what does it mean to choose delta 2 as an odd multiple of m pi? That means k0 n2 d2 must be equal to some odd value of m into pi. I know k0 to be the free space wave vector, which is given by 2 pi by lambda 0, where I denote this lambda 0 as a special or the wavelength at which you are choosing this condition to be true. Okay. So please note that if you take a different wavelength, okay, this condition in general will not be true, and therefore for that wavelength the transmission will not be peaked, but in fact there will be a large amount of reflection. Okay. So in fact this phenomenon wherein the transmission is peaked at certain wavelengths can be used to resolve those wavelengths. Okay. If you have a slightly broadband wavelength and you want to separate only a particular wavelength lambda 0, you want to pick only that lambda 0, then if you choose delta 2 appropriately and the value of the finesse, then you will be able to just remove that portion of the wavelength or that portion of the spectrum around the wavelength lambda 0 and leave all the others reflected back. So you can actually pick wavelengths from this, or you can separate or resolve wavelengths from this. Okay. So that is major use of a Fabry-Perot cavity. It can be used as a filter or it can be used as a resolving element. Okay. So coming back to what should be the distance d2, don't be surprised if you actually see a familiar expression now. So k0 is 2 pi by lambda 0, n2 d2 will be equal to some m times pi. Pi on both sides can be cancelled out, and what you have, oh sorry, you actually had delta 2 here. Delta 2 was k0 n2, so this is all right. So we have actually written this one correctly. So if I now look at what is d2, d2 will be equal to m lambda 0 divided by 2 n2. Okay. And remember that this lambda 0 by n2 is actually the wavelength in the medium. Okay. It is the wavelength in the medium, and then wavelength divided by 2 if you choose. For this choice you will see that the transmittivity actually peaks. Okay. So this distance d2 is kind of twice the quarter wave transformer distance. Okay. So that is something that I wanted to point out. Okay. I would actually ask you to solve this same problem not in terms of these matrices, but in terms of the transmission line analogy that we have already talked about. In this case the transmission line analogy is very simple. So you have a film, and then with the impedance of eta 0, which is the air impedance, and inside this material or inside the film is actually captured as a transmission line with a distance d2, okay, with a distance d2 having a characteristic impedance of eta 0 divided by n2. Okay. So if you actually look at what is the overall effective impedance and then calculate the corresponding value and then set the required value for d2, calculate the reflection coefficient and then obtain the transmission coefficient, set the value of d2 such that you achieve this condition, you will end up having the same condition as we have derived from the matrix approach. Okay. But when you go to multiple layers, matrix approach is easier to program, and therefore that is the approach that we are going to take care of. Before we leave this subject, there is one small case that we need to talk about. We have so far assumed that in the film or in the Fabry-Perot cavity, light was incident normally to the surface. What if light is incident at an angle? Well, if you incident light at an angle, then you have to consider two cases. One is the transverse electric case and the transverse magnetic case, right? That is TE and TM polarizations. And in place of that small r that we wrote, you have to replace that R by the appropriate reflection coefficient corresponding to TE or TM, and in place of delta 2 it won't be this delta 2 which is equal to K0 N2 D2, but rather the corresponding component which is normal to the surface, which means there has to be a cos theta angle, right. So that would mean you replace this R with either RTE or RTM appropriately, which both of them depend on the angle of incidence, and then you replace delta 2 by delta 2 cos theta I, where delta 2 by itself is given by K0 N2 D2, okay, D2 being the thickness of that particular layer, okay. I would also like to introduce couple of additional terms that we talk about. So we have already seen that when delta 2 is equal to m pi, right. So we had sin square delta 2 equal to 0, and the transmittivity at this particular m pi value when delta 2 is equal to m pi was equal to 1, okay. And we said that this can be achieved, right, at a particular wavelength in fact, okay. So wavelength can be related back to frequency, right, by the phase velocity. So instead of writing K0 as 2 pi by lambda 0, I can write this as omega by up, where up is the phase velocity of the wave inside the Fabry-Perot cavity, okay. And because there is a number m here, or the subscript m, so we will also subscript the value of omega, okay, telling us that when delta 2 is equal to m pi, that actually happens at a specific frequency of omega m, okay. So the condition delta 2 equal to m pi means that omega m n2 d2 divided by, well, I wrote c, but in general it could be any phase velocity, right. So it could be phase velocity, well, but because I have already written n2 over here, so this was actually correctly written as c itself, okay. If not, I could combine n2 and c and write this as up, the phase velocity. So this would be equal to m pi, okay. So when your frequency satisfies this condition, then delta 2 will be m pi, sin square delta 2 is equal to 0, and consequently the transmittivity will be equal to 1, okay. The same condition can actually occur when delta 2 can be equal to m plus 1 into pi, that would be the next peak in the transmittivity. So at that peak, let us say the frequency is omega m plus 1 and remaining everything is the same. And now if you look at the difference between these two frequencies, so there is a difference between delta omega, which is given by omega m plus 1 minus omega m, and this will be equal to c by n2 d2 times pi, okay. So rewrite omega m as 2 pi into fm and then obtain the frequency difference delta f, and you will see that this would be up divided by 2 into d2, or you can write this as c divided by 2 n2 d2, where up is c by d2. And this frequency delta f, which tells you how periodic in terms of the frequency that the Fabry-Perot cavity is called as the free spectral range, okay. So this is all about the Fabry-Perot cavity. I will leave as an exercise what to do about FSR in terms of wavelength, okay. So you find out what is the expression for FSR in terms of wavelength. Well, you just have to replace these conditions by 2 pi by lambda m plus 1 and 2 pi by lambda m, and appropriately adjust or find out the value of delta m. One of the important uses of the Fabry-Perot cavity is this. So I have this Fabry-Perot cavity like this. If I am able to move the second arm, right, not the medium, second arm slightly, then on the fly I can actually change the value of d2. So as I change d2, and if the input frequencies or the input wavelengths remain the same, where the Fabry-Perot cavity was resonant at the frequency earlier would not be the same resonance frequency because I have changed d2. So earlier d2, this was resonant at some omega m. Now when I change it slightly, that same omega m, the Fabry-Perot cavity would not resonate, and hence would not allow the transmission of that particular frequency. It will allow transmission into a new frequency. So in fact, if I can slightly scan this second arm, I can go over a broad wavelength, picking up each frequency individually, or the group of frequencies with very sharp transmission peaks, I can pick them up individually. So this device, which makes use of movement of one of the arms in order to resolve the frequencies or find out all the frequencies in the supplied optical spectrum is called as a Fabry-Perot scanning interferometric spectrum analyzer, or simply Fabry-Perot scanning interferometer. Okay. The reason for interferometer will become clear shortly, where we now consider the case of a multi-layer films. Multi-layer films are no more difficult to deal than the single layer films. The general structure would involve something like this. In general, you can have the distances to be very different. So, let us say D1, D2, D3 and so on. You come in with light at an oblique incidence, right, and there will be a reflected light as well, and into the second medium this light would propagate, right. So, this light would propagate and hit at a certain transmission angle theta t. So, you have an incidence angle theta I into from the incident medium, and then in the first film, right, you will have a certain transmission angle. How do I calculate theta I and theta t, or rather how do I calculate theta t from theta I? The relationship between these two at any interface is given by Snell's law, right. So, I apply Snell's law over here, where I am also assuming that these refractive indices are n1, n2, or rather sorry, outside is n1, n2, n3, n4 and n5, right. So, you notice here that there are actually 1, 2, 3 and 4 total layers. So, this is an example where we have considered 4 layers, and how many films are there? There are only 3 films, right. So, there is a film 1, film 2, film 3. Incident medium and the transmitted medium are essentially the same, okay, or you can actually have a substrate down here and outside would be a different medium, but you will have 4 layers, 3 films, and there will be 5 interfaces to work with, and therefore you have to place one S matrix or the transmission matrix that we have talked about at each of the interfaces. So, S3, S4, I am sorry, there will be only 4 interface matrices, whereas there are actually 1, 2, 3, 4 interfaces. Sorry, this is 4 layers, actually I mean by 4 interfaces. So, this is actually 4 layer, 3 film, 4 interface. The number of S matrices required for this one will be 1 to n. In general, for a n layer, n minus 1 films. Okay. If you consider n films, there will be n plus 1 layers, and therefore there will be n plus 1 matrices. Okay. And what are the electric fields here? So, this would be E1 incident, E1 reflected, or rather E1 plus, E1 minus. There would be, because light went inside here, there would be an angle of incidence which is actually related to theta t in the second layer. Then there will be a reflection. Similarly, there will be incidence and reflection onto every medium. So, this is E1 plus, E1 minus. So, this would be E2 plus, E2 minus, E3 plus, E3 minus, E4 plus, E4 minus, and finally you have E5 plus usually, because I do not have any incoming radiation from E5 minus. Okay. So, you can write down a matrix for each of them. So, at the jth interface or the ith interface, the matrix Si will be equal to 1 by Ti e to the power j delta I r I e power j delta I r I e power minus j delta I and e power minus j delta I, where of course delta I is given by k0 ni in the ith layer or the ith film that we are talking about. So, it would be k0 ni di being the distance times cos theta I. So, please note that this is not the incident angle, but this is the angle which the light makes into that appropriate film. Okay. So, from the appropriate film, this would be the value of delta I. In the most general case, these multilayer films are used especially in what is called as optical coatings in order to make mirrors and filters and reflectors, and the theory of optical coatings is wide. It involves optimization, it involves lot of mathematics, not just the matrix approach that we have considered, and it is an extremely important design problem in optics community. The basic idea is to use these matrices, or in cases to incorporate polarization, you have to modify these 2 by 2 matrices into 4 by 4 matrices, but that is essentially a big optimization problem which we do not have time to cover. Okay. But very quickly I will tell you what are the types of these multi-layer films that are used. For more details I will give you references which you can refer to. Okay. If you build a 5-layer stack or a 4-layer stack, okay, to eliminate reflection, what would happen is, if you look at the single layer reflection, you would see something like this. So this is a single layer AR coated material. So you will have a substrate out there and there will be a coating material here, and this is air, let us say. So when you incident light, if this coating material is of single layer, then this is the kind of reflectivity that you see as a function of wavelength. Okay. So clearly you are not doing a very good job of removing reflections. On the other hand, if you actually do a multi-layer coating with appropriately chosen values, which I won't tell you because it's an extremely difficult problem to talk about that, then what happens is that the reflectivity is actually very low, which means that in this entire region there is a complete transmission. So this is the job of an AR coating, to transmit completely, and that it does with very low reflectivity and over much broader wavelength than a single AR filter can be. Okay. In optical WDM components you come across what is called as filters. Okay. We will have more to say about this filter technology when we talk of WDM component thing, but these filters are called as interference filters. What these interference filters do is that you have an alternate stack of high, low indices. In between you will have either for a low or a high, does not matter. So I just picked arbitrarily at low here, but you could in fact have a high refractive index. Each of these layers are of lambda by 4 thickness, but please remember the lambda that we talk about is the medium lambda. So you will have to look at the corresponding refractive indices to actually find out what is the corresponding lambda, and then do that lambda by 4, and then again follow up with the stack of alternating H and L. The stack of alternating H and L will cause the reflection sign to differ. So which means there will be a phase of pi, and depending on whether you adjust the phases to be in such a way that they can constructively interfere in the incident medium or interfere destructively in the incident medium, you can have a highly reflecting stack or you can have a highly transmitting stack. Okay. Both type of filters are used. One is the transmitting filter, one is the reflecting filter, and these interference filters, because the reflection sign changes plus minus because of the high low thing, and because of lambda by 4 thickness, each one-way propagation will be a pi by 2 phase, two-way propagation will be a pi phase. So you can adjust the phase difference, and because of the partial reflections and the interference among the partial reflections, you can have a complete transmission or very near complete transmission or very large reflection over very broad wavelength regions. Okay. So these interference filters we will have more to say in the WDM components. Thank you very much.